All right, so welcome back. We are going to continue our discussion of motion today. Towards the end of the lecture, we'll cross out any sort of important announcements to be made. So we're just going to jump straight into the content. What have we been studying? We've been studying this idea of motion and this way to specifically quantify motion. We want a way to mathematically make an analysis of motion, because once you can mathematically make an analysis, well, then you can start to make predictions, and making predictions can be a very powerful thing that we can do. So, going back to our ideas of motion, looks like last time we stopped by talking about position, displacement, velocity. That's about there. So as a quick refresher on last time, well, we started with this idea of position, and we looked a lot at these one-dimensional positions, and for today we will be sticking to the one-dimensional case. We're going to deal with two-dimensional motion a little bit later on. So your one-dimensional motion, it might be horizontal, left, right. It might be vertical motion, up and down. During our motion, we said we must define some origin, right? Whenever we are talking about the position of an object, we're talking about the location the object is relative to some origin. So in any case that you are studying motion, well, an origin needs to be defined. The origin where you are deciding that that location has a position of 0. On this horizontal, I put it at this little middle-ish point. Why? Well, because it's arbitrary. I can choose. It can be left, right, middle. It doesn't matter. On the right-hand vertical axis, I put the origin at the bottom. Again, it's arbitrary. Doesn't matter where you put it. And at that point, your position can be marked as being either positive or negative. That positive and negative is important. That positive and negative tells you about the direction. Position is a vector, and we need a direction in order to say, without ambiguity, where something is located. Because if I said something is located perhaps 2 meters from the origin, so we'll say 1, 2, 1, 2, and each of these are in meters. If we say an object is 2 meters away from the origin, well, 2 meters away could mean one of two different things. 2 meters away could mean negative 2 meters, that is 2 meters from the origin. Or it could be 2 meters on the other side. Both of those are 2 meters away. So you need a way to specify direction. That's where that negative and positive come into. That's the importance of the vector here, to reduce the ambiguity when we talk about something like position. Because when you say something is negative 2 meters, that leaves only one possible location, 2 meters to the left. If you say the vertical position is positive 3 meters, we have 1, 2, 3 meters up. If you say the vertical position is positive 3 meters, that means without ambiguity, the location is right there. So the direction tells you, without ambiguity, where an object is. Now, knowing where an object is only the first step of understanding motion, understanding the position. The next step is understanding the displacement. Displacement, I'm going to shorthand it. Displacement is a description of how that position has changed. And we define our position to change with some delta symbol. Delta means change. It's the Greek symbol delta. It's a triangle. Greek symbol delta means change. We might say change in position X. This is a horizontal change. Or perhaps change in position Y. That is a vertical change. And how do we mark this? Well, we mark our change in position, our displacement, to be a final minus an initial value of our position. Y final minus Y initial. So that gives us our displacement. It tells us how has our position changed. This is crucial for motion, because when you're talking about motion, you want to know how the position of any object that you are analyzing, how the position changes. And after that, we moved on to say, well, we might want to know how quickly does that position change? How quickly does the position change? So you look at this displacement, you figure out how long did that displacement take, and you can define from those quantities a velocity. You look at how quickly the displacement happened. The displacement happened in 1 second, 2 seconds, 3 seconds, however long it happened. This gives you a velocity. Your velocity we traditionally represent with a v. Well, your velocity is going to be displacement divided by the time it took for that displacement to happen. Now, you might have something displacing vertically, moving up and down. You might have something displacing horizontally, moving left and right. So what we might want to do is to define some v subscript x. And it says this is our horizontal velocity. What does this mean? This means we are strictly looking at the velocity of an object that is moving left and right. We would say that an object moving in this horizontal dimension, we would say that this has some velocity, vx. So we say this is specifically the velocity's x component. We go back to this idea of vectors, right? Vectors had x and y. This is the x component of your velocity. And how do we find that? Well, it's no problem. We just take our displacement in the horizontal direction and we divide it by the time that it took. That's how we define the horizontal component of our velocity. And we say, well, what if we're moving vertically? If we're moving vertically, we would say, well, v y. Y is a perfectly good subscript to use for up and down motion. So if something is moving in this vertical dimension, we might say it has some y component of velocity, delta y over time. And then we say, okay, well, what if we're moving in the third dimension, right? We haven't really talked too much about the third dimension. Third dimension would be z. We can say that there's some z velocity. What would that be? That would be something coming out of the screen, coming straight out at you. This is your third dimension, moving forward and backwards. Well, what would that be defined as? Well, delta z over t. When you talk about the different dimensions, all of the dimensions are going to be symmetric. All three dimensions are symmetric. The equations don't change just because you're looking at a different dimension. The equations will always be the same. The only difference is we're substituting out x for y or x for z. All of the dimensions, though, they're mathematically similar. They're mathematically equivalent. This is going to be very powerful for us a little bit later on when we start talking about motion that is occurring in multiple dimensions. But as I said today we're going to focus on motion in a single dimension. We're going to focus on one-dimensional motion. And specifically what we are going to look at is what occurs when we start to look at some object that has non-constant velocity. So we are going to look at an object that has a changing velocity, meaning your velocity is non-constant. Because everything we did last time assumes a constant velocity, but what happens if it's not constant? This is an important question because most things in nature don't travel at a constant velocity all the time. Most objects will, at some point in their life, speed up, slow down, even change direction. All of those are cases where your velocity is non-constant. So we really want to analyze this question of what happens when we change velocities, okay? Well, how do we do that? We might first start off by thinking about how we would define some quantity that describes for us a change in velocity. And we take inspiration from how we described our changing position. We said, well, we defined some physical characteristic that was given by the change in position over time. So we might say, whatever this quantity is that describes a change in velocity, why don't we just say that it's change in velocity over time? Why do we do this? Well, this gives us a way to see how quickly does our velocity change, right? If t is small, then we have a very fast change in velocity. If t is large, then we have a very slow change in velocity. So this seems to be a good way to describe some change in velocity. And I'm going to put in delta v over delta t. The reason I put a delta there is just to show you some symmetry later. We don't usually include it in our equations, but I'll keep it here for the moment. So we say this is a quantity that describes our velocity changing. This is a quantity that describes how our velocity changes. This would be our acceleration. I ran out of room there, but that is your acceleration. Your acceleration defined to be your changing velocity over time. Traditionally, we use acceleration A, the letter to represent acceleration. Makes sense. First letter of acceleration. We say, why not? Then we look at this and we say, well, A is delta V over delta T. I'm going to write delta V over T for a second. This is how we typically might write it. Or delta V is your final velocity minus your initial velocity. Deltas always mean final minus initial. We look at this and there's one important thing I've been neglecting here. Velocity has direction. So it's a vector. Well, if velocity is a vector, then acceleration also has directionality. Acceleration also has a direction, meaning acceleration is also a vector quantity. Giving us our fourth quantity of motion. Okay. Well, we look at this and say acceleration is delta v over delta t. That's wonderful. We look at a graph, perhaps. Sometimes it's good to look at things graphically. We did this in lab this week. Look at all of these different velocity versus time and position versus time graphs. When you look at velocity versus time, if you were to imagine an object speeding up, let's say an object starts at 0 velocity at time t equals 0. And over time, the velocity increases. So we get an increase in velocity over time. You get an increase in velocity over time, and we maybe look at two different points in time. Let's say this is t final, t initial. Whatever those times are, I don't know, I don't care. They just exist. It's 1 second and 3 seconds, or 2 seconds and 4 seconds. It doesn't matter. We look at what those points are represented on at these curves. On this curve, on this line. It's not a curve yet. And when we do that, we see that our delta t is represented by the run between those 2 points. Your delta v is represented by the rise. Well, what does that tell us? That tells us that acceleration is simply the slope of our velocity versus time growth. So what do? We say our acceleration is our slope of our velocity versus time growth. Seems reasonable, yes? All right. Well, we could use this to our advantage. We say acceleration is the slope. We have a straight line here. A straight line tells us what? A straight line, mathematically, y equals mx plus b. Again, you go to your algebra teacher, you ask, what's the equation of a straight line? That's what they'll tell you. Y equals mx plus b. But that's the mathematician way to write it, with some arbitrary value y, some arbitrary value x, with no meaning behind either of those values. In physics, we give meaning to these values. So we say in physics, it's not y, it's not arbitrary y. Instead, it's a very real quantity. It's the quantity we have on our vertical axis. Well, what do we have on our vertical axis here? What is this quantity? Velocity. So we get our velocity, v. All right, so we have velocity is our y-axis characteristic. Okay. M, that is your slope, but we just said something about our slope. What did we say about our slope? It's acceleration. So instead of M for slope, we write A for acceleration. All right, and then we look at this. The mathematician would say arbitrary x. But the physicist says, no, that x has meaning. What is the meaning of your horizontal axis there? Time. And then your math teacher would say, B is your y-intercept. But to the physicist, no, B means something else. B is the value that your vertical axis takes at time t equals 0. This is your first moment velocity. This is your initial velocity. The initial. And the physicist will then tell you that this line is not represented by y equals mx plus b. Rather, it is the mathematical model that will predict what the velocity is at any time in the future, given you know how it started and you know what the acceleration is. So we take a look at this and we say, okay, well, how does this model work out? How does this model work out? Let's go ahead and start thinking about things more analytically. Let's assign some numbers to this. So what we're going to do here is imagine an object that is accelerating. Sound good? We imagine an object that is accelerating. We say that over time, this object will speed up. We say over time, this object will speed up. Let's say the object we track at a time of 0 seconds, 1 second, 2 seconds, 3 seconds, so on. All right, well, it's going to be speeding up, right? So we say that the velocity is going to change, right? We say at the beginning, perhaps we have 0 meters per second. We include our unit. We make sure to always include our units with numbers. This is our starting velocity, but is this going to be our velocity forever? No. It is not our velocity forever because we are accelerating, we are changing. Perhaps we say at 1 second we are moving with a velocity of 2 meters per second. And since there's a positive value, that positive value indicates for us direction. Right? Because, well, I didn't have to include the positive on the 0. The positive and negative 0 is the same thing. The positive 2 meters per second, that implies that it's moving to the right at a velocity of 2 meters per second. Okay. Well, what about 2 seconds? Perhaps it's moving at 4 meters per second. And then at 3 seconds, maybe it's moving 6 meters per second. And then at 4 seconds, how fast are we moving? Can we make a prediction? 8 meters per second. How do we know that? How did we come to that conclusion? Who wants to raise their hand and tell me how they came to that conclusion?
It seems like the acceleration is constant.
The acceleration is constant. And what is that constant? 2? It's changing by 2 each second, right? So what we can say is that our change in velocity is going to be 2 meters per second every second. So our acceleration causes a change in velocity that is 2 meters per second every second. Now, this is a very wordy way to write something. So instead, what we might do is take this and write it more mathematically. How do we do that? Well, we write it by saying it is specifically adding 2 meters per second every 1 second. I'll put the plus sign out here. It is adding 2 meters per second every second. So we take this sentence, we're adding 2 meters per second every second, and we take that and we turn it into a mathematical equation where we are saying we are moving 2 meters per second every second. Now pop quiz, 2 divided by 1 is? 2. Wonderful. We're all math pros here. We know 2 divided by 1 is equal to 2. And then we look at the second part. We have meters per second per second. We can rewrite this. We can say this is meters per second times 1 over second. Or even better yet, we can combine those two units of second. We can combine those 2 units of second to give us 2 meters per second squared. So we have this new quantity that describes our changing velocity. This new quantity that describes our changing velocity, and what did we say is the quantity that describes changing velocity? We said that that is our acceleration. This is the physical meaning of what acceleration is. You get a number for your acceleration. What that number means is how much your velocity is changing every second. So if you have an acceleration that's 2 meters per second squared, that is saying every second the acceleration causes a change in velocity of 2 meters per second. So we think of another example. Let's say we do another chart, but this time what if we don't know the velocity? What if instead we know what the acceleration is? Let's say we track an object for a few seconds, 0, 1, 2, 3, 5, and 6. And these are all in seconds, so I will specify seconds. And now what we're going to do is we're going to consider an object that is undergoing constant acceleration. Constant acceleration. Acceleration, which will have units of meters per second squared. All right, and what is that constant acceleration going to be? Well, I'm going to say it's minus 10. Why not? Okay. Constant acceleration means the acceleration is unchanging. So at 1 second, what is the acceleration going to be? Negative 10. What about at 2 seconds? What's the acceleration? 3 seconds? 5 seconds? 6 seconds is also negative 10. Constant acceleration means that your acceleration does not change. Your acceleration does not change. But does your speed change? Absolutely. Does your velocity change? Absolutely. Your velocity changes. Because you are accelerating. So let's look at an example. Let's say we start out at positive 30 meters per second. That is our initial velocity. Or our acceleration says that we change by negative 10 meters per second every second. So what would our velocity be at 1 second? Plus 20. What about at 2 seconds? Plus 10. 3 seconds? 0. 5 seconds? Minus 20. 6 seconds? Minus 30. So we think about this motion, and what does it tell us? It tells us that we start off moving in the positive direction quite rapidly. We move in the positive direction, but as we do, we slow down. At 3 seconds, we come to a stop. And afterwards, we start moving in the negative direction. But what occurred in this motion? We're moving to the right, come to a stop, and what do? I change direction. I turn around. When you have these values, where your velocity is 0, but you have acceleration. Yes, you can have 0 velocity, but still have acceleration. And when you have these 0 velocities with acceleration, they occur because you are starting off going in one direction, a positive direction. And you end up going in another direction, a negative direction. And to go from positive and negative, you have to pass through the numerical value that separates your positive values and your negative values. You have to pass through 0. We call these, in physics, we call these turning points. Because they are the points in which you turn around. And they play a pretty big effect in various areas of physics. Do we feel okay about this? Any thoughts and comments? I think it can often help us to make graphs. I love making a graph. So what we'll do here is we'll graph out two things. We will graph out first the acceleration versus time. For our object that is moving with an acceleration negative 10 meters per second. Oops, I should have made this negative. So we graph out our values. And we say, okay, well, at time t equals 0, our acceleration was at negative 10. Second later, 1, 2, 3, 4, 5, 6 seconds. Second later, it's going to be negative 10. Second later, after that, negative 10, negative 10. It's always going to be negative 10. You end up with a horizontal line. Your acceleration here is a horizontal line. Anytime you have constant acceleration, your acceleration versus time curve quote unquote, will be a straight horizontal line. We then take a look, well, what is velocity versus time going to look like? Velocity in meters per second over time in seconds. We mark off 1, 2, 3, 4, 5, 6 seconds. And we say, what is our initial velocity? 10, 20, 30, negative 10, negative 20, negative 30. We mark off our points here. We say we start off at a positive 30 meters per second. I think that's what I said. And then a second later, we move to 20 meters per second. And then we move to 10 meters per second. And then we move to what is our velocity at 3 seconds? 0. What is our velocity at 5 seconds? Negative 20 meters per second, absolutely. Negative 20 meters per second. Then we have negative 30 meters per second for our 6th second. Does that sound good? Do we all see this? Now, had I done a good job of actually marking out my axes, this would have formed a straight line. Straight-ish. It would have formed a straight line. And we start to see our velocity versus time curve, and what do we notice? We notice that we spend some time in the positive realm, in the positive quadrant. When we're in this positive quadrant, that tells us that we are moving in the positive direction. The part that's below the curve, this is in the negative quadrant, right? Negative y, but positive x. This is in the negative quadrants. This tells us we are moving in the negative direction. We are moving positive, and then we move negative. And between moving positive and negative, what do? We turn. Your turning points are represented in that x-intercept. The x-intercept is when you turn around, where your line crosses through the x-axis. That is the moment that you turn around. Okay. We go a little bit further. We say, okay, well, I understand calculus to some degree. I know my calculus relatively well, and well enough to say that when we're looking at velocity versus time, the rate of change of velocity, how quickly your velocity changes over time, that rate of change of velocity, by calculus means, must be the slope of this line. So we look at it and we calculate the slope. We say rise over run. Perhaps we use this. We use whatever 2 points we really want to here. It looks like I picked the third point, 2 seconds, 10 meters per second, and the last point, 6 minus 30. Look at this and we say, okay, well, what is going to be the rise here? Our rise, we go from positive. Oh my gosh, I really did not do a good job on this graph. We look at rise over run. If we look at the third data point and the last data point, our rise goes from positive 10 to minus 30. To go from positive 10 to minus 30, you have to go down 40 meters per second, yes? So your rise is negative 40 meters per second. If we look at our run, we go from 2 to 6. Well, that's a run of 4. Rise over run, negative 40 over 4 gives you negative 10. Negative 10 being your acceleration. So absolutely, the slope does still give you your acceleration. The slope of the line gives you your acceleration. We feel okay so far. What questions are out there? Anybody got a question? All right. Well, we think about calculus a little bit more. We think about calculus a little bit more, and we say that our acceleration is the slope. What does that mean? The acceleration is the derivative of velocity with respect to time. That's the calculus definition of a slope, right? Under the limit that delta t goes to 0, the slope, or the rate of change, is found by the derivative. That's your fundamental theorem of calculus. But I can take this and I can rearrange this equation, right? Just because it's a derivative doesn't mean I can't do algebra. So what I'm going to do is rearrange this equation. And I'm going to write acceleration multiplied by dt is equal to dv. And I'm going to drop my vector arrows just to be lazy. But these are still vectors. Sound good? And we say, well, dv and dt, these look suspiciously like integrals, like antiderivatives, right? An antiderivative of dv, that's just going to be your delta v. So what does this tell us? This tells us that our change in velocity is given by the integral of acceleration with respect to time. Now, yes, you can, and we will, do a little bit of work with the algebra, or more specifically the calculus of it. But when we think about integral, one of the things that should come to mind is area under the curve, right? When you're going through calculus, integral is just a fancy way to sum the area under a curve. An integral is just a summation of our areas. So we look at this acceleration versus time graph. We say the integral of that the integral of acceleration with respect to time should give us delta v. What does that mean? That means that the area that exists under this curve, which is your integral, should give you delta v. Well, what is the area of this curve? The area of this curve is going to be a height of negative 10 meters per second squared and a width 60 meters per second. Oh, sorry, no, 60 seconds. 6 seconds. Oh my God, what am I doing? I was spoiling, I was jumping ahead to the answer. But we have a height of negative 10, a width of 6. What is the area? Negative 60. Negative 60, you do negative 10 meters per second squared multiplied by 6 seconds. Your seconds, one of them cancels out with the denominator of meter per second squared, and you get negative 60 meters per second. This should be your change in velocity during this 6 seconds. When we look at our velocity, we started at positive 30. We ended at negative 30 meters per second. What is our change? Negative 60 meters per second. So what does this do for us? What we did is we showed, well, the slope did give us our acceleration. Meaning that we did prove this first part, that the slope gave us acceleration. We took the slope of velocity versus time, we got acceleration. Wonderful. The second thing we just did, by finding the area under this and finding that it is our delta V, we proved this second equation. That delta V is the integral of area, acceleration times delta T. Feel good about this? Any questions? And here's where things are going to get a little bit mathy. But don't worry, I'm doing this to derive for you guys a couple of equations. And from those equations, once we do this derivation for those equations, then they're yours free to use. You don't have to rederive them. But I do want to show you that these equations come from someplace fundamental. So we always want to make these mathematical models. We want to make these mathematical models so that we can make predictions about motion. And a place we often want to start is with acceleration. And for simplicity, we will start with acceleration being a constant value. What is that constant? It could be anything. It could be 1 meter per second squared, 2 meters per second squared, pi meters per second squared. Doesn't matter. Your acceleration is some constant value. Well, if this is true, then delta V is given by the integral of acceleration dt. If acceleration is a constant, then that pulls out of the integral. And the integral of dt just becomes delta t, which means that your change in velocity can be mathematically analyzed by looking at your acceleration and multiplying it by your delta t. We look over here and that makes sense. If we look over a change in time of 2 seconds and we multiply our acceleration by that delta t, our acceleration is negative 10, multiplied by a 2-second delta, that would be negative 20 meters per second. We see that we do have a change in negative 20 meters per second. That makes sense. That gives us something that works with what we've done so far. We move on to say, well, this, or more commonly written, V final is equal to V initial plus acceleration delta t, where I just break that delta V up into being V final minus V initial, pull that V initial over to the other side. This can be taken one step further. We can say that if it is the case that velocity is the derivative of position with respect to time, and that is something that we saw last time and we talked about at the very beginning of lecture today. If this is the case, we can do the same exact thing we did with our acceleration to give us that our change in position, delta x, in other words, our displacement, is given by integral v dt, what we had earlier. Similar to what we had earlier with our acceleration. At which point we say, okay, well, delta x is equal to the integral of velocity dt. We just found an equation that will tell us velocity. What is it? Well, our equation that tells us velocity is going to be our initial velocity added to our acceleration multiplied by time. v initial plus acceleration times, I'm just going to reduce my delta t to t here to save room on the board. But we have our change in x being the integral of velocity times time. Plug in for velocity is v initial plus acceleration times time. We get this relationship for our displacement, the integral of v initial plus at dt. For those of you who have taken calculus and feel good about your calculus, you can go ahead and do the work to show this result, but I'm just going to go ahead and give it to you. This integral solves out to be v initial times time plus 1/2 the acceleration times time squared. This gives you a second equation. A second equation derived from this idea that your acceleration is constant. This first equation and the second equation are considered to be your two kinematic equations for constant acceleration motion. These only apply under the case that your acceleration is constant. This only applies when your acceleration is constant. And that does include acceleration being zero, a non-accelerating object. These equations still apply because zero is still constant. So we get to this point. The last two lectures have really built up to this. The last two lectures have built up to giving us these two equations for constant acceleration motion. V equals v initial plus acceleration times time. X is equal to x initial plus v initial t plus 1/2 acceleration times time squared. From these two equations, we can further derive other equations. We can take these two equations and combine them, for example, algebraically to solve for any one of these variables and to cancel them out. We can take these two equations and combine them to be, for example, v final squared is equal to v initial squared plus 2a times x final minus x initial. You just have to do algebra to get to them. But this gives you a third kinematic equation for constant acceleration. How do we do that? How do we find that? The way you would find that is to take this top equation, solve for time is equal to your change in velocity over acceleration, and then plug that into the bottom equation for any place where you see time. It's just an algebra problem. You can get other kinematic equations. You can get the kinematic equation that, I'm going to write delta x here, but that's just x final minus x initial, is 1/2 v final x, actually I'm just going to put v final for a second, plus v initial multiplied by time. And then you can get a third kinematic equation, a third derived kinematic equations from the top two of delta x is equal to v final times time minus 1/2 the acceleration times time squared. And these are generally speaking considered to be your kinematic equations for constant acceleration motion. These 5 equations can be useful in different contexts, and we'll go through a couple of them just in a moment. But what we can see is that some of these equations have different variables than others. For example, this third equation makes no reference to time. So if you're given some problem where you don't know what time is and you don't care about what time is, this third equation is a great choice. Or let's say you know what the ending velocity is, but not the starting velocity. This last equation might be helpful. So each of these models are different, are applicable in different senses. So you might be given questions of the form, a car accelerates at a rate of 12 meters per second. A car accelerates at a rate of 12 meters per second. How long passes before the car reaches 36 meters per second? This is probably a pretty easy question. You can probably all answer this off the top of your head. Make a prediction and tell your neighbor what you think that the time will be. Just real quick. Turn to your neighbor. Tell him, how long do you think it's going to take? All right, so we have guesses being made. We have guesses being made, and we often like to start problems by doing this, by taking a guess at what you think the answer is going to be. Make a hypothesis, in other words. Then what we do is we approach this problem by analyzing what kind of problem is this. Whenever you approach physics, it's important to ask yourselves, what is going on? What is the concept? What is the physics? And here, the concept is kinematic motion with acceleration being constant. By undergoing this analysis, you know then that it must be the case that these 5 equations are going to apply to this problem. These 5 equations apply to this problem. Next thing you might want to do is write out what known values you have, what unknown values you have whenever you're approaching a problem. Keeping a list of known values is helpful. Because reading a problem, I meant to put a squared here. Reading this problem, we can then pull the information out and it changes a word problem into being a mathematics problem. So you say, okay, reading the problem, I know acceleration is 12 meters per second squared. Reading the problem, I know that my final velocity is 36 meters per second. Reading the problem, I can infer that the initial velocity is 0 meters per second. That comes from language cues. Inferring the 0 meters per second is important. And then I ask myself the question of what am I looking for? What am I looking for? I'm looking for time equals something. Make sure you always keep your goal in mind. It's easy to go down rabbit holes, especially as these problems will get more and more complicated throughout the semester. So you say, what am I looking for? I'm looking for time. Once you understand what you have, what you're looking for, you can then move on to figuring out what equation you want to use. We look at these equations and we'll go from the bottom to the top. This last equation, I know my acceleration, I know my final velocity, I'm looking for time, that's all good, but it makes reference to a displacement. I don't know what my displacement is. So that last equation is no good, there's 2 unknowns. You look at the second to last equation, again, displacement and time, 2 unknowns. 2 unknowns is no good. You look for the equation that will have just a singular unknown. This next equation, again, a displacement I don't know, and an acceleration and a v initial, v final. Well, I know my acceleration, my v initial, my v final. This third equation only has 1 unknown. This third equation is usable. This third equation can be used here. It has just one unknown, a delta x, a displacement. We look up to this second to the top equation. Again, a delta x and a t unknown that's not usable. And then the top equation has one unknown. Top equation can be used as well. And this is where it's important to keep in mind what you're looking for. Because we have two equations. There are two equations that are usable. We can use and implement either of these two equations, but which one do we want to use? The top one. Why do we want to use the top one? Yeah, that's the one that has the quantity that we're looking for, the time. So we choose to use the top equation, and we deduce that we want to use this top equation because the only unknown it has is the unknown that we are looking for. So we write down that equation. We say, okay, I'm looking for time, so I will algebraically solve this for time. So you take our final velocity, subtract off our initial velocity, and divide by the acceleration. We plug in the values now. Once we have an expression that represents what our time will be, we plug in the values that we have. We do 36 meters per second minus 0 and divide by 12 meters per second squared. 36 minus 0 is 36. 36 divided by 12, 3 seconds. And I should put 3.0 there for sig figs. No, not meters per second. We just have it in a second. 3 seconds. That's probably what we predicted, right? We predicted this. We predicted this because we're good at understanding patterns, and we understand the pattern that should be there. The numbers might get more complicated, at which point the math becomes more important. But in this case, we're able to find the answer relatively quickly. Any questions about this? Feel all right about it? We might ask a different question. We might change the question slightly. We might ask, how far does it move before the car reaches 36 meters per second? We change the question slightly. What does this do? This changes what we're looking for. This changes what we're looking for. We're now looking for the displacement. But just because we change what we're looking for doesn't mean that what we did a second ago doesn't apply. Because it's still true that this motion will take 3 seconds. Just because we change what we're looking for doesn't mean that the scenario changes at all. The scenario is the same. It will still take 3 seconds to get there. So we can absolutely have solved for that 3 seconds, even if it's not what's directly being asked for. Now what's being asked for is going to be your displacement, your change in x in this case. If we look at their equations, we look at the top one. Well, there are no unknowns in the top one. That's because we used it already to solve for time, but there are no unknowns, so it's not particularly useful. We look at the next one. X and x initial, that is our delta x. V initial, t, and a, we have the second equation, usable to find delta x. Third equation, we have our final, our initial velocity, and our acceleration. It's usable to find delta x. This fourth equation, delta x is 1/2 v final minus plus v initial times time, usable to find delta x. In fact, all of them are usable to find delta x. So we just pick one that we want to work with. It doesn't matter which you pick. You should get the same result. So if we wanted to, we can say delta x is equal to v initial times time plus 1/2 acceleration times square. We might choose to use that one. All right, well, v initial is 0. V initial is 0. 0 times time is going to be 0, because anything times 0 is 0. And what this would mean is that we have 1/2 our acceleration, 12 meters per second squared, multiplied by our time, 3 seconds quantity squared. We pull out a calculator, we do 1/2 12 times 3 times 3, and you should get pull out your calculator, do it real quick. Make sure you get the same thing as me. Okay, double check my work. Did you guys get 54 meters? Wonderful, perfect. So, doesn't matter which kinematic equation you wanted to use. You get the same result. Now we're going to talk about another type of motion that is constant acceleration motion. We're going to talk about the motion of free fall. Free fall is motion that occurs when an object is only under the influence of gravity. It is falling only under the influence of gravity. What does that mean? That means it's in the air. It's moving through the air. So here's the problem that I'm going to propose to you guys. You've just taken your physics test, and you want to get back at your professor for it, so what you're going to do is you're going to drop a balloon on his head from 25 meters up. Question is, how long is it going to take before it hits its target? Ultimately, this is just a wordy way to say how long does it take for an object to fall 25 meters. Now, what's interesting here is that it does not matter what object you're looking at. So long as air resistance is negligible, and that's what we mean by free fall, we're saying that we can neglect air resistance. As long as air resistance is negligible, every single object would take the same amount of time to fall this distance. And that's because every single object would fall with the same acceleration. And what is that acceleration going to be? Well, the acceleration due to free fall motion is negative 9.8 meters per second squared when you're near the Earth's surface. If you go up to very high altitudes, you might get to a point where it's 9.7 meters per second. Won't sufficiently change. Okay. It won't sufficiently change, but you would have an acceleration about negative 9.8 meters per second squared anywhere that's really habitable. So we have this acceleration for our free-falling object. Now, since every single object falls with this same acceleration, we do give it a constant to represent. We give it the constant represented by the letter g. And we say that letter g represents a positive 9.8 meters per second squared. Yes, we use the positive value for our representation of this gravitational constant. We use the positive value because there is time when you might consider downwards to be positive, and this just erases the ambiguity. This says g is always going to be a positive value. And if you're solving for something where you say positive is up, then the acceleration that that object feels is going to be negative g. And then we start to think about how we approach this problem. And then you start to worry because we define these kinematic equations for the horizontal direction. Everything was in x, right? Everything was horizontal. But here's the good news. The dimensions of motion, up, down, left, right, forward, back, they're all equivalent to each other mathematically. Since they're all equivalent to each other, where we have a delta x is equal to v initial times time plus 1/2 at squared, we could get the same exact result, but with our y direction. We could have derived that delta y for our vertical direction is v initial times time plus 1/2 at squared as well. But we have to be careful here now. Because in both of these equations we represent v initial. We want to be specific. We want to say this is our initial x component or our initial y component. So we might write our equations a little more carefully to denote that I'm specifically talking about the y component of our velocity or the x component. Same with acceleration. You might say x acceleration, y acceleration. Come over here and you might say this is the acceleration in the y direction, because things that you drop accelerate up and down. I've never seen gravity pull something to the left, so pretty sure it's safe to say acceleration for free fall is always going to be vertical. Does that sound good? So we then have this kinematic equation. We can also represent other kinematic equation. V final y squared is equal to v initial y squared plus 2a y times y final minus y initial. Just swap out your x's for your y's. And now we can approach this problem in the same exact way we did earlier. Same exact way. Now we say v initial in the y direction. Well, if you drop the balloon, it starts at rest. Dropping an object, it starts with zero velocity. And if you ever see the word drop, that means you're releasing it. It is starting from rest. If you see the word throw generally means that it doesn't have zero velocity initially. We look at this and we say, well, what is our y initial? Our y initial, if you define 0 to be the target's head, y initial is 25 meters above that. Y initial is positive 25 meters. Y final, 0 meters. And your acceleration in the y direction, is negative g. So then the question is, what becomes of the time? What is the time? And a note on time, in each of these equations, you don't need to put a subscript on time because time isn't a dimensional quantity as far as x and y. Time is just a scalar quantity that represents passage of events. So you don't need a subscript on your time. So here's what I want you to do. I want you to calculate. How much time passes for the balloon to hit the professor's head? Okay, I've given you your third slip of paper now this semester. This one is for your kinematic equations. All right, don't yell out your answer, but raise your hand if you have an answer. Raise your hand if you need a little more time. Okay, give you guys a moment. All right, quick show of hands. How many of us got an answer now? More of us, more of us. What did we get right?
2.3 seconds.
2.3 seconds. 2.3 seconds. And how might you find that? Well, you look at your kinematic equations, and perhaps you look at the kinematic equation that says that delta y, y final minus y initial, your delta y is given by v initial times time plus 1/2 your acceleration times time squared. Take a look at this, and why might you want to use it? Well, I know my v initial is 0. I know my acceleration is negative 9.8 meters per second squared, and I know my delta y. So we take a look at this and we solve this. Time would therefore equal the square root of 2 times delta y divided by acceleration. Delta y is negative 25 meters per second. Delta y is negative 25 meters. Acceleration is negative 9.8 meters per second squared. You plug this in, you get time is equal to what? Go ahead. If you haven't already, plug it into your calculator. Make sure that you guys can use your calculator's different functions. Some of you guys have already done it. In 2.25 seconds, what you got earlier, right? Now, there are different ways to approach this problem. There are multiple paths. So there's 5 kinematic equations. So undoubtedly, there's multiple ways you can solve it. For this problem, sig figs, 25 has 2. We will always consider 9.8 to be an exact number. Your significant figures will never be limited by that 9.8. So here, since our significant figures is 2 from that 25 meters, we would write 2.3 seconds for the correctly rounded value. All right, then we look at another problem perhaps. Let's say we toss a rock upwards at 29.4 meters per second. Question is, how much time passes before it hits the ground? How much time passes before it hits the ground? Well, in analyzing this problem, it's another kinematics problem. Another kinematics problem with the acceleration being negative g. What are the things that we know? We know v initial. V initial is going to be a positive, because you are throwing it upwards, a positive 29.4 meters per second. It's a positive 29.4 meters per second. Then we look at this and we say, well, what else do we know? Well, not much. V final, do we know V final? Does not hit the ground at 0, right? If we track this rock, right, we have time 1, 2, 3, 4, we'll say 5 seconds, we'll track it, 4. The velocity, actually I'll start with 0, 1. The velocity in meters per second. At 0, it's going to be 29.4 meters per second. At 1, what do we do? At 1 second, we subtract 9.8. So it's 29.4 minus 9.8. 19.6 meters per second. Does that sound right? All right, then we look at 2 seconds. Subtract off another 9.8. What do we get when we subtract off another 9.8? Get 9.8. And then at 3 seconds, we subtract off another 9.8. We get to 0. And then at the 4th second, we subtract off another 9.8. But what's important here is that you're not at 0 when you hit the ground. Because what do we have? We have an object that's moving upwards. It's moving upwards. It continues to move upwards. It continues to move upwards until it reaches that 0. This 0 point is not when it hits the ground. What that 0 point actually is the turning point. Remember, when the velocity is 0, you're at a turning point. And what this turning point is the moment that it goes from traveling up to traveling down, going from positive to negative. This turning point is the point at which the object reaches its highest location. or its highest position, if you'd rather. So 0 is not when it hits the ground. 0 is actually the highest point. Yes?
Do we know like how tall the person is throwing it, or are they throwing it from like 0 meters, or?
We'll assume 0 meters. We'll assume 0 meters. Before it hits the person, change the question a little bit. Throws it up, it's going to come down, hit him in the head. So what else do we know? Well, we know, what else do we know? We know its initial position. Its initial position, we'll say, is 0. Its final position is 0. We describe the starting and ending point to be the same. It's arbitrary. If the person is a meter tall, we could say y initial is 1 meter, y final is 1 meter. Your initial, or your origin is arbitrary. But what is important here is that the starting and ending position are the same. Your displacement, your delta y, ends up being 0. So those are your known values. Question is, what is the time going to be? And to find out the time, simply apply some kinematic equations. I'm going to leave this as a exercise for the reader. You guys are going to go ahead. I want you to try and solve this before next time. It's just a nice free fall equation. Okay, are there any questions before we head out? Any thoughts, comments, concerns? All right, you guys do have homework due to me, so be sure that before you leave today, you turn in your homework, turn it in at the front desk right here.